We'll start again, and I think this is pretty much where we got to a few minutes ago, so let's move on. So what do we have to consider when we're thinking about power and ground? Well, we need to think about maximums. How much current do we need? How much current are we allowed? Corners and local discontinuities. So there's one thing having a nice straight bit of wire. Of course, when you go around to a corner, in detail, it behaves slightly differently, and you can get hotspots, especially when a power line changes level. So remember the way the circuits look. You've got multi-metal layers, and they can be joined together with little plugs, but these give you discontinuities in terms of local resistances and so on, which can then become hotspots. And we need to think about the density and the width of the tracks. Electron migration is a really important thing. We'll come to that soon. And yes, when you're actually designing, there will be process guidelines. In other words, the factory, the fab will have certain design rules which have to be followed, because otherwise the system won't work. So this is what you might think as being a nice net of power distribution or whatever, but actually that doesn't work terribly well. So let's think a bit about a circuit. You're going to have some areas where you don't need a lot of power, and some areas on the circuit which are going to need more power. It's just the way things are. Some areas will be infrequently used, for instance, whereas other parts of the circuit will be used all the time. And therefore, some places need thicker wires, some you can do with thinner wires. So you could then have something like this, where you've got your power in a nice big thick wire, because all the power is going through here. Of course, as you move towards the end of the distribution, you get thinner and thinner because you're using less power. And so essentially you're optimizing the wire thickness and the width of the wires are really for constant current density in all the tracks. So that's one way of doing it. But another way you can look at it and say, well, actually, we could have multiple power in, and you'll see that in many chips. So they don't just have a single input for power, they have several inputs for power. So here we've got one at each corner. So then when you start to work out your wiring, you can end up with thinner tracks because you've got less distance to go from the supply to the target. And so actually that can save space internally in your design. So here's an example chip, and there are multiple grounds, multiple power inputs. So here's the ground, for instance, here, but there's another ground up there, another one over here. And of course, likewise for the power distribution, which is VCC in this diagram, you've got one here and you've got another one here, for instance. So typically you can have more than one, and that makes life easier for the design. So the power used by the gates, we've looked at this already a little bit, depends on the capacitance. So how do we work out this capacitance? Well, essentially, we need to add up all the gate lengths and widths. Well, the gate length is usually the same across the whole chip. So it's the different gate widths which are important here. And we then use the parallel plate approximation, which basically says you've got an area, and then you've got your permittivity and your thickness of the oxide. And so therefore you're adding all your widths of your N transistors and your P transistors and you multiply by L, and so on. So that gives you your capacitance. But you've also got a capacitance for the tracks. So you've got your wires, and there are various design rules which constrain what you can do, and they give you information about the interconnect capacitance between different layers. So let's draw some of these wires. So you've got two lengths of wire here, one there and one there. What you'll see is that you've got two types of capacitance. You've got a capacitance within the plane between this wire and this wire. And you've also got a capacitance between planes here. So we're lumping it into two-dimensional and linear coefficients. So the 2D is between plane and plane, and the linear coefficient along the length of the track. So this one, the K1, the 2D, you've got the length of the track, but also the width is important because that gives you this capacitance to the underneath layer. Of course, you have to think about the upper layers too. And then for the tracks, it's slightly different because you've got the length. The width here doesn't come into it. Of course, you do have a thickness here, but that's not under your control. So you get a vertical capacitance due to the track area and a horizontal capacitance caused by the track length. So then you can work out some sort of average power consumption, and you could say, well, the average power consumption is going to be P average is going to be CV squared D, sorry, CVD squared times the frequency, where the capacitance is what we've just worked out from the gates and from the wires. But not all the gates turn on and off at every cycle. So what we need to do is to include some sort of stimulation rate, which varies between 0 and 100%. And so we end up with this sort of equation here. So there are different stimulation rates for different parts of the circuit, and therefore the equation looks again a bit more complicated. So we need to know the stimulation rate for each node, each part of the circuit, and we need the capacitances at each node. And this is quite hard to do by hand because you not only need the physical layout, which is the hardware of where all the tracks are, but you're also then going to need software information about how the chip's going to be used. And of course, this then depends on assumptions because the stimulation rate will vary a lot between whether you're doing some word processing, for instance, on your laptop, or whether you are on a Zoom call or watching a video or playing a game or whatever you're doing. So generally speaking, you need automated tools to help with this sort of process. And these tools are very sophisticated these days. But here we at least getting some idea of what the tools are doing and what the calculations are. Let's move on to electromigration, because this is something which can be a major problem. So essentially, a wire has lots of metal ions in it, and they've got different forces on them. So there's the force which comes from the electric field. So of course there's an electric field in the wire, because that's what drives the potential difference which drives the current. But also you've got the, if you like, the collision of electrons like a wind, and they're going in the opposite direction from the electric field, and they are pushing into the ion. And eventually ions can get displaced from their original location. Now, this is something you don't want to happen, but you can get whole grains of metal physically dislodged. And then two things can happen. Either the track can break because a section of it has just physically moved and become disconnected from the other sections, or else that if you get this electromigration, then the two tracks can actually end up touching each other. So electromigration is worse at high temperatures. So if you have a hot spot on the wire in your chip, then you will have a worse problem. So here's a picture showing these two situations. So we've got a void up here. So there's a metal track and there's a gap. So that will give you an open circuit. And then this hillock caused by a grain moving, and that can cause short circuits with neighboring tracks. And clearly these are both critical failures which you don't want to have. So essentially, in VLSI design, you're trying to maximize the amount of current you can get through your tracks, but you need to keep it within limits. Now, in a wire, the current flow tends to be in one direction. And that tends to make it worse because the force is always in the same direction. So power supply lines and grounds tend to have unidirectional current flow. But also in some of our CMOS devices, you've got the same situation. So for instance, if you look at an inverter, there's a DC current component, which is always flowing from the VDD to VSS. The other thing to note is that electromigration is much more severe in aluminium, and it's reduced if you add a little bit of silicon to the aluminium, which is what people did originally. They said, well, we add some silicon, it strengthens the aluminium in the sense that there's less electromigration, so that's good. In the last 20 years or so, silicon technology has moved on, and generally the wires are now made of copper, and this is a better conductor than aluminium, and so therefore the temperature increases are less, electromigration issues are much smaller, but they're still there and it needs to be taken account of. Okay, so how do we do some calculations around this? So we need to estimate the current in the track. So we have a total capacitance and an average power, which we looked at before. And then we can say, well, there's an average current, which is just simply going to be power divided by the voltage. Alternatively, and more accurately, we can start looking at peak currents. So for instance, at clock edges, the current's going to be much higher than anywhere else. So that's clearly an important thing to look at, but that is harder and needs some simulation. So there are going to be some design rules. We need to think about the highest possible operating temperatures, which is normally about 125 centigrade. We generally end up with a rule of thumb which says you can have a certain amount of current per width of track. Now, in principle, you might say, well, it should be current per unit area of the cross section, because that's what gives you the resistance and resistivity. But the thickness isn't in the control of the designer. So from the designer's point of view, having a rule of thumb says maximum current density per micron of width is useful and gives us a general feeling of where we need to do or what widths we need to use. So this number 1 milliamp per micron was typical for aluminium. Actually, for copper, it can be about 10 times higher, which is clearly a huge advantage. The reason it took a long time to move from aluminium to copper is that copper was much, much harder to process, but standard processes are copper now. This number 10 milliamps per micron is a typical number for DC, unidirectional. If you've got bidirectional, then again, you can have greater numbers, and again, an increase of an order of magnitude is possible. So what you need to do is to route your tracks to have enough width to minimize the current density. And that's fairly easy to do. If you know what the maximum current density is, you can work out the width fairly straightforwardly. There are second order effects here. In other words, if you say, well, my calculation says I need a wider track, well, then the wider track will add capacitance to the system, and that extra capacitance will add more current, and you need to make the track wider again. So you need to, as I say, look into this iteration process. And finally, use copper. And essentially, all major fabs use copper these days because it's got greater current handling capacity. So if you look at a chip, here we have a cross-section of a chip. So what we've got is the bottom here is the silicon. And what you can see for the most part are your copper tracks. So physically, the chip is mostly metal and insulator, and all the transistors are in this tiny little area down here. Okay, that's it. That's the transistors, that little tiny bit at the bottom. And what you can see is these metal layers get thicker as you go up. So you have great big thick wires up here for power and more local wiring down below. And then these are plugs which take you from one level of circuitry to the next. Of course, you see not only are the metal thickness is getting bigger, but the spacing is getting bigger to improve the capacitance. So how do you reduce track capacitance? Well, the basic equation is that the capacitance is equal to the area divided by the thickness. So that's the thickness between one layer and the next. And then here we have the dielectric constant or permittivity, or also called K. So this then gives us the idea of low K dielectrics. And Americans who don't like too many letters will miss out the W and have low K. And of course, you can have the opposite, which is high K. We'll come to that later. So low K gives you lower loss. The permittivity is lower. And that then reduces the power consumption in your interconnects, and that reduces your delays. So how can you reduce the dielectric constant or permittivity? Essentially what you do is you replace, instead of using silicon dioxide, which was a straightforward, fairly easy insulator to use other insulators which have lower dielectric constants. And typical ones are aerogels, which, as the name suggests, contain some air. And with lower density comes lower dielectric constants. And also you can use polymers. Of course, there's a limit to how low you can go. So the dielectric constant, for instance, of silicon nitride is about 1.9. Silicon oxide, you're getting lower than that, but you can't get below 1. So a low K dielectric might get you to 1.2, 1.3, but you're not going to get any lower than 1, which would be a vacuum at the very best, and you can't build a circuit with vacuum, so you need to have something there. So that's low K dielectrics. Don't confuse these with high K dielectrics, which are used around the gate area, and we'll come and talk about that another week. Another issue to consider is ground bounce when designing a system. So our systems, as I've said, typically will have a clock. And so they're synchronous, and they have pulses of current at the clock edges. And of course, if you've got a pulse of current, then the voltage will drop when the current is drawn. And you then have some EMI implications. So essentially what you have is mutual inductance. So a current coming and going in one wire will induce a current in another wire. And so what you can do to solve this is you can have some decoupling, which of course is another capacitor which adds capacitance, but it does smooth out some of this ground bounce problem. You can also do something called pseudo-random clocking, which again adds complexity to your design. If you have different clock phases in different parts of the chip, and that then means that you don't have the whole chip with a clock edge at the same moment. Another big area we need to think about is input and output. So up to now, we've been thinking about our inverters, our bigger gates, adders, multipliers, and so forth. But we can't connect a signal from one of these logic devices to the outside world, because these tiny transistors which we're building are very sensitive, and they just almost certainly be destroyed instantly. Moreover, they don't have the drive strength to drive the outside world. They're made as small as possible so they can drive another logic gate within our circuit, but they don't drive an external system. They don't have standard logic thresholds, so our chip might be in a system which runs at 3 volts externally, but internally, its logic threshold would be very different. So the thresholds are different, the voltages are different, so it doesn't match with our PCB. So you can't just simply connect our gate to the outside world. So what we need to do is to have some buffer in between the circuit and the PCB. The other thing that needs to happen is we need to physically connect to the package, which is done by a wire bond, or sometimes by flip chip bonding. But both of these need big pads, which are of the order of 100 microns or 50 microns. These are huge compared to the size of our gates. And we need some sort of protective I/O ring because of static or whatever. You don't want your chip to be easily destroyed simply by handling or whatever. So this gives us the idea of a digital I/O pad, which is used for both input and output. So it can be reconfigurable, can be used as either one or the other, and that's quite often used in, for instance, a microcontroller. When you think about it as input characteristics, it's got to have adequate electrostatic protection, typically 2 kilovolts per millisecond, which is 2 joules. It's got to be sensitive to the right threshold, so that's the external circuit thresholds, and external circuit signals have got to work going in. Output, we've got the same sort of problem. It's got to have an adequate drive strength, and it's got to match the threshold voltages for the outside world. In both cases, it's got to meet correct speed requirements, and it's going to be a big circuit compared to these little tiny transistors we've been looking at for the VLSI circuit, so it's going to be power hungry as well. So here is our diagrammatic pad. So this is a large square, typically of metal, which can be bonded to the outside world with wire bond. That's typical. So I say 50 or 100 micron square, pretty big. But then it needs a protection circuit. And then it also needs various inverting and non-inverting buffers. And so we need to match the drive strengths to both the outside world and the circuit on the inside. So that's relatively straightforward. So here we are. Here's a typical design that's done for this. So we can see that we've got an enable signal and a data signal. So essentially, these things work in tri-state. So we can either have it as a high impedance, or we can have it as an output or as an input. And so we've got the world of the world of the VLSI chip, which we've been talking about at this end, and the pad here, which goes to the outside world at the other end. We've also got the same circuit. Okay, so this circuit here, I've just redrawn here. So you can see the same transistors, M1, M5, and so on. The M3 and M4, between them, simply form a pass gate. So that's been drawn as a pass gate with our enable signal. So the enable signal here can either be high or low, and this clearly will either enable the pass gate, or the other way around, or disable it. So it's not a pass gate, it's a transmission gate. So then we can think about the two different states. So we've got either enable is 0 or enable is 1. So if enable is high, then essentially this gate is enabled, so it transmits both directions. And then we have M1, M2, M5, M6 form essentially two inverters, and that's our amplifier going out. If the enable is low, then that will turn M5 off and M7 off, and essentially the pad becomes high impedance. So, okay, it needs a reasonable number of transistors, but it's a relatively simple circuit and does the job. So that is the output circuit. You also need an input circuit. And you need a protection circuit. So here is the protection circuit. So you've got the pad, and you've got your protection circuit here, and then your buffers. So an incoming signal that's coming in here. What have you got? You've got two transistors, N and P, and two diodes and a resistor. So it sees these two transistors. What it actually sees is the parasitic bipolar transistor. So if you remember, right back at the start, I mentioned this, and you can look up details in textbook if you want to. But essentially, if you've got a MOS transistor, so take an NMOS, you've got N for the source and the drain, and P for when it's undoped for the gate area and the body. And this essentially looks exactly like a bipolar transistor. Normally, when you're using these transistors, the MOSFETs, they're biased in such a way that this parasitic bipolar is inactive and not doing anything. But here, the whole circuit is being designed around the parasitic bipolar. We want it to do something. So when a voltage surge comes here, either one of these two parasitic transistors will turn on, and the high voltage will be dissipated to ground. And you've got some low pass filtering, and the idea is you want a voltage protection, typically within 0.7 volts of your ground and VDD. So the way the surge protection works is by impact ionization. So normally, as I said, you design a MOSFET to minimize the effect of the parasitic bipolar and to make sure it's biased in such a way that it never turns on. But in this particular case, what you're wanting to do is to maximize the effect of the parasitic bipolar, because that is what you're going to be using to take away the current spike, which comes from a voltage spike. So essentially, you've got either an NPN or PNP bipolar, depending whether you've got the NMOS or the PMOS. So this one shows the NMOS one. And if you've got a large positive spike, it'll reverse bias and the voltage is big, you get impact ionization. So basically, impact ionization is when an electron, free electron, which is one of your conducting electrons, because the large electric field, the electron is accelerated, it scatters, it collides with something, and because the large electric field, it has gained enough energy by then to ionize the next atom. In other words, it creates another electron hole pair, and this creates an avalanche in the end, and you get a huge current, and the large voltage spike is dissipated. So that's roughly how it works. We don't need to go into the details too much for this course. So that gives you the protection from electrostatic discharges. Right, the next area we want to look at is test circuits, because design for test is pretty essential. So in other words, we design our CPU, our microprocessor, whatever chip we've got, and it needs to have some sort of self-test built into it so that we can actually tell that it works. So if you're buying chips from Intel to build your laptop computers, so you want your Intel microprocessors to work. So if there's some sort of test standard and test method, you can do that. So the standard one is the level sensitive scan design, LSSD, and this enables chips to be tested. And essentially what you're doing is you're looking at all the key logic parts of the chip and making sure that they're working. So how does that work? So if you've got logic, and we've seen these pipelines before, you have registers before and after. Excuse me. Be very quick, I'm trying to give a lecture. Sorry. Sorry, somebody coming in and distracting me. Let's try again. So we have the scan chains going to be organized. So the idea basically is that you've got two modes. You've got a test mode and a normal mode. So scan equals 1, this assert data here, basically puts it into a test mode and lets each section be tested using a scan in port. So essentially there's a scan in port, which will be a single pad input to the circuit, and you can put the data into that in a serial fashion. So you basically clock in your test data and then run it and make sure that when the test data is into the register, then the logic behaves in the way you want the logic to behave. And then you can scan in the next bit of data and test that as well. So in other words, you can test your logic sections for a large number of different types of input and make sure that it works. And then when you put scan to 0, the system reverts to normal, and you're just clocking data through the logic in the normal way, and the system behaves as intended. So that's the basic idea. We're wanting to have two modes, test mode and normal mode. And in the test mode, you have a scanning the input data, and of course you need to scan out as well, so you can check that the outputs are what you expect them to be. So how do we go about arranging that? So you want your test words coming in here. And essentially, when it says scan in, the register is going to be filled bit by bit with the data you're using for the test. So supposing it's a nice simple 8-bit register, typically it might be a 64-bit register. You're scanning in each bit of the register, so 8 or 64 clock cycles to set up the data. And then it passes through the logic chip, and then you're reading it out in the scan out here and checking that this particular logic block did what you wanted. And of course, you can do the same with this logic block here. So it doesn't use many terminals because you're putting this data in and getting it out in a serial fashion. So it's not a big overhead in the chip design, but it does enable a lot of the key functions of the chip to be tested. So how do you build your scan register? Because essentially it's a register which has two forms of behavior. It behaves as a normal register with data coming in and then going out. Or if you're in scan mode, the data is coming in this way and then through here and then this way again. So if you look at a data register, it's simply a row of D-type latches. And each latch is clocked simultaneously. So what we can do is we can wire it up like this. And then this is the standard way of doing it. So whatever the input word was, the next clock cycle, that's the output one. So that's what we've seen already. But you can wire it up differently. If you wire it up this way, then what happens is your clock is ticking. And every time the clock ticks, the data, instead of going as a word in and a word out, but one bit comes in here and it gets sent to here. Then that bit moves to here and to here. So if you've got a stream of bits coming in here, then eventually each latch will be given a different bit, different value, and you are setting up your test word for the device. So the bits are shifted left to right. So a scan register, what it needs to be able to do is both those things. It needs to be able to take data from your input word and send it to the output word, but it also needs to be able to send data through in this direction. And the way you switch it is by using this scan line here, which comes, to signal to each of these multiplexers. And that then lets you choose what's going into D. So D can either be the input from AI here, in which case this one's got BI coming in, this is CI, this is DI coming to it. So you've got your data word going in, your data word going out, or you change the multiplexer and the data is coming from this here to D, and it's acting as a scan register, and the bits are moving from here to here to here to here. So simply by changing scan from 0 to 1, you can change its operation from a normal data register to a shift register. So it can be one or the other. And you can draw that at the transistor level if you want. So these are our half latches. There's one here and one here. And then we've got our scan-in with our two transmission gates to make the multiplexer. And this is one small section of the whole device. So this shows how you do it with a C² latch, but clearly you can do it with other types as well. Okay, there are other ways you can do this. So, but IBM defined a LSSD with 3 separate clocks. They had a normal clock, they had a scan clock and a slave clock. So you can see you've got 3 half latches put together. And the way to think about this is that either so it forms a complete latch between them, a level sensitive latch, level sensitive latch, level sensitive latch, but 2 of them together make an edge sensitive latch, and those 2 make another edge sensitive latch. And so you're essentially choosing either this one or this one. So a normal operation, clock B is off, and clock B is the scan clock. So that's off, then this latch is doing nothing, because if B is permanently 0, as your clock into a half latch, then the output is just high impedance. And therefore, you just simply have these 2 half latches working together, and the system runs as a normal latch. However, in scan operation, you reverse things. Clock A is turned off, clock B is turned on. And then what you're doing is you're running these together. You then run it at a test speed, which is slow. You're putting in your data in a different way. But this also is a way you can clock different data into the system, depending on whether your scan clock is operational or not. So this is an alternative route, but essentially this form of testing is standard and built into microcontroller, microprocessor, ASIC type designs. Okay, so our power consumption, in summary, we need to know what the power consumption is. So we need to calculate it. And once you've calculated it, we can then figure out how we can distribute it. For the clock distribution, remember clock tree was a nice way to distribute the clock across the whole chip. Power nets were slightly different design, but they're also important for distributing the power across the whole chip. Latches, phases, skew, these are all really important things we've been looking at. We looked a little bit at I/O, the pads and the rings, because those are really important to match the internal logic with the big harsh world outside. And so it's important that you have these I/O pads. And when we talk about an I/O ring, the basic idea here is that around the outside of your chip, you have a whole ring of these pads, because typically you'll have many contacts to the outside world. And then finally, we had a quick look at LSSD, which is used for testing purposes to verify that the product actually works. So say physical layout next, but actually next Friday, we're going to go over the second tutorial. So the second tutorial is on the wiki, not on the wiki, on the Moodle. You'll find it there. I think put the dates on it wrongly. I need to update those correctly. But we will be doing those 5 tutorial questions next Friday, and you should be able to make a good attempt at them, and it will do you good to spend time working on them. So I'll see you then. Bye.